our network, which represents our town. So we've got the houses as the nodes and the paths as the links, and each link has a length. Now, here I've described a simple algorithm for this problem, and it might actually look something like the basic method that you sketched out earlier. However, we don't expect you to be able to come up with an algorithm like this yourself from scratch. So don't worry, I'm just presenting the algorithm here so you can see what one looks like and we can run through it. In that way, hopefully you can begin to understand how to construct your own algorithms. So the problem can be summed up as follows. Given the network made up of nodes and weighted links, which links should be included or excluded in order to achieve the lowest total weight, the lowest total path length, while ensuring that the network is still connected, that is, that no houses are isolated. So we're essentially deciding whether or not links are in or out of the final network. So we start with none of the links included and gradually add them to a new network or mark them as being included by essentially paving them. And as we just said, a requirement in the problem is that we need to be able to visit any house wherever we start on the network. So we have this idea of marking houses as either visited or not visited. So you can actually mark them as visited on the sheet by ticking off the letter label, and we start with a situation where none of the houses have been visited and there are no paths selected at all, and that's our initial state. So none of the houses are marked as visited. So we start just by picking a random house. It doesn't matter which one, as they're all equally important in the network. Nobody's house is more important than anyone else's. So we then mark that house as visited since we're now on it. Then we have this repeat until structure, which is a fundamental control structure in algorithms, and it basically says keep doing this thing until some condition is true. So in this case, it's keep doing the next two lines of the algorithm until all of the houses are marked as visited. That is, we've fully connected all of the houses together. So this repeat until basically says keep doing these two things until we've marked all of the houses as visited. So we repeatedly do the following. We look at all of the possible paths that connect any visited house to any unvisited house, since the important thing is to make sure that we can visit all of the houses. And it's also important that it's all such paths, not just the paths connecting the current house that we're on. So we gradually grow a set of available links, okay, which connect any visited house to any unvisited house. And then we pick the shortest path out of that available set of paths. And then that's our next path to add to the new network. And then mark the house that it connects to as visited, since there's now a path to it, and in turn that new visited house potentially opens up a new set of paths, and the process continues until we've been to every house. Okay, so hopefully that's clear in terms of the basic structure of the algorithm. You essentially pick a random house, look at the available links that connect it to any other unvisited house, add those to the set of available links, choose the shortest one, and carry on. Now, if you have a set of links that are all of the same length and they're all the shortest length, so for example, if you've got a bunch of links that are all of length 3, just choose one at random. Okay, so now what I'd like you to do is essentially run the algorithm on the network. So again, I've made the worksheet available as a PDF, so hopefully you've managed to print this off. But what I want you to do is basically follow these steps, okay, keeping track of houses that have been visited and the available connections between them, okay, and hopefully you'll come up with a network that looks like something like the solution that we came up with before. If you get stuck or if you can't work out what to do, then simply unpause the movie and I'll go through it with you shortly. But have a go yourself first. Okay, so now I'm going to step through the algorithm so you can see how it works in detail. So I'll use the following conventions. The visited nodes are greyed out, so they're covered with a sort of grey circle. The paved paths are shown in purple, and the available paths, that is any path that connects a visited node or a house to an unvisited node, are shown in red. I apologise if this colour scheme causes any problems for anybody, but I'll try to highlight them manually with the pointer as well. So we arbitrarily select A to start with and mark it as visited, so we grey it out. So these three links here, here and here then become available to us, so they're connecting A to an unvisited house, B, E and F. Okay, so these three links are available to us. One is 2, one is 3 and one is 4, so we have to select the one that is of length 2 because it's the shortest. Okay, so we add 2, this link, to the new network, follow the link to house B and mark B as visited. Now we've extended the set of possible paths to add this one of length 4, this one of length 5 and this one of length 4. Okay, as that again connecting a visited house to an unvisited house. Okay, however, the shortest link in that set of paths is this one here of length 3 connecting A to E, so we add that one to the network, follow it and mark E as visited. Okay, so we've moved to E and we've added this link to the new network. In turn, moving to E opens up these three new paths, this one here of length 4, this one here of length 4 and this one here of length 2. So this latter path is now the shortest path in the set of all paths that connect an unvisited house to a visited house, so we take that one. So now we're at F, we've marked F as being visited and we've added 2 4s, this one here and a 3. So you can see how the set of available paths is 4, 5, 4, 4, 4 and 3. So there's a 3, that's the shortest, so we have to take that one. So we take the 3 from F to G and we mark G as visited. Now, so here we have a 4, a 5, a 4, a 3. Moving to G adds these connections here and you can see how there's a 2, which is the smallest in the set, so we have to take that one. Now, we have a couple of 5s, a bunch of 4s and some 3s. We could pick any of the 3s, and that's where indeed we get the two different solutions from. So in this case we just pick one of the 3s at random. In this case we randomly pick the path from H to J. This gives us a 2 in our available set, which we have to take, which moves us to I. Now, you can see that moving to I actually removes this edge from consideration, this link from consideration, because it's now connecting two houses that have previously been visited. So we can't consider that link anymore. However, we have a choice between 2 3s now, so you can see how the available and the same applies. Sorry, the same applies to this edge. This link here, it's no longer available. Neither is this one, because they all connect houses that have been visited before. So now we have a choice. We've got a 4, a 5, a 4, a 5, and 2 3s. So we have to choose one of the 3s at random. So we choose the G to D and add that link to the network. So now with the D, that leaves us with a final choice of 5, a 3 and a 4. Well, obviously the 3 is the shortest, so we have to take the 3 connecting D and C. And when we take that path, C is the final house to be marked as visited, and the algorithm is complete. So what we're left with is this structure here, which we call a minimum spanning tree. So a tree is a specific type of data structure. Essentially it's a network without any loops, and the minimum just means that it's as small as it can be, and spanning means that it touches every node. And the algorithm that we just walked through is called Prim's algorithm. It was originally invented by the Czech mathematician Wojciech Czarnek in 1930. It was rediscovered by Robert Prim in 1957 and by Edgar Dijkstra in 1959. So this algorithm actually has a very long heritage, and yet it's still used today. It's what's known as a greedy algorithm, as it always looks for the shortest available move at any one time step. So these algorithms are relatively simple and often efficient, but they sometimes don't produce the best results, as they're quite short-sighted and can't look a few moves ahead to see if there's a better combination of moves. So, this lecture has introduced quite a few concepts that we'll use later on, such as the idea of storing a number of things such as houses or nodes or the paths, each of which has information attached to it, such as a letter label or a weight or the fact that it's visited or not. And we also introduced the repeat until control structure, which allows us to keep doing something indefinitely until some condition is met. We came across the idea of flipping an attribute or a piece of information from one state to the other, that is a house that's been visited or not. And we saw the idea of calculating a list or a set of options from those available. So just to wrap up, we've continued the theme of computational thinking by showing how we can embed or encode a description of the real world and a problem in the real world by simplifying it and showing how it can be represented in a data structure, the network, that makes it amenable to solution by an algorithm. So we then walked through an algorithm for solving that specific problem. Again, remember, none of this needed any code as such. The algorithm was the important thing. If you want to think a little bit more about some of these issues, which will involve stepping through the algorithm again in a bit more detail, then follow the link to the Extra Challenge movie. Otherwise, I'll see you next time.